Hi and welcome to Popcorn Electronics. In this video, I'll make a voltage-tuned variable frequency oscillator with complete design and analysis. In my view, these are the four most popular variable frequency oscillators used by homebrew enthusiasts today. I will not discuss the VXO or variable crystal oscillator. I think that's a video unto itself. They are a valid VFO that you may consider. The LC or inductor air variable capacitor VFO is the holy grail VFO. The problem today is finding and or affording an air variable main tuning capacitor. The enemy of the LC VFO is temperature drift. Building a frequency or temperature stable VFO is no small task for a newcomer. To that end, I made a video focusing on temperature coefficients to enable newcomers to make frequency stable LC VFOs. The video is on my other channel, and I'll link that video down below. In the permeability tuned oscillator, or PTO, the capacitance remains fixed and there's a variable inductance. The variable inductor usually consists of a single layer of wire wound around a coil former, which could just be cylindrical plastic. A metal piece passes in and out of that coil of wire to vary the inductance. Typically that's a finely threaded bolt, so you turn the bolt in or out just like you would a normal tuning dial to vary the inductance and, of course, frequency of the VFO. PTOs can be built inexpensively. Perhaps you're a craftsman type person who's good with their hands and tools. Maybe you've got a 3D printer to make the coil former. The PTO might be a great option for your receiver. The last image was a PTO built by Bill N2CQR, who's the leader of the SolderSmoke podcast and blog. On his blog, under Topic Index, lies great information on the PTO. My very first ham receiver, a Drake R4C, had a PTO and it drifted 400 to 600 Hz per hour. My best homebrew PTO was at 5 MHz and it drifted 300 Hz per hour, and I'll admit I'm not a good craftsman. The SI5351 CMOS or digital VFO remains a powerful and popular local oscillator in the homebrew toolkit. I have 3 gripes with the SI5351. First, they're rarely sealed in an RF-tight container and spew forth abundantly. Second, compared to an LC or a PTO type oscillator, they use a lot of current. I do know some of that is the digital display and that you could leave that off and so forth. And thirdly, they're a bit of an appliance. What about making an LC VFO with special variable capacitance or Varactor diodes? Voltage tuned VFOs are frequently used with phase lock loops to lock them into one frequency. What about just leaving off the PLL or phase lock loop? That's what I did for this video. My goal was to beat the 300 Hz per hour temperature drift of my best 5 MHz PTO. Do you think I reached my goal? Let's review my design goals. The fundamental frequency is 3.5 MHz. An external doubler will double it to 7 MHz, which is a technique used in 7 MHz direct conversion receivers, and I'll show you both the 3.5 and 7 MHz outputs. I'm a CW or Morse code operator. I seek a tuning bandwidth of at least 50 kHz. Both the tuning bandwidth and drift will double when we convert it to 7 MHz. In a typical oscillator, a JFET offers lower flicker noise and better immunity to temperature drift than a bipolar transistor. However, I'm going with a transistor radio. I seek an output power of at least 10 dBm, and there is no schematic. This is a complete design and build on my bench. This schematic is broken into 2 halves. The Varactor diodes and their tuning circuitry lie on the second half. Q2 is a standard popular voltage regulator referenced by a 7.5 volt Zener diode. It functions as a stable low-pass filter to provide clean and stable DC to Q1, our oscillator transistor. I'll just jump to this slide for a moment. Q1 and Q2 are BD139 medium power audio transistors. These have an FT of about 190 megahertz, making them very useful for homebrew HF projects. Note there is one radio frequency choke, or RFC, and that's 15 turns on an FB432401 toroid. That's basically just a fat FT3743. Why did I use a BD139 for Q1 and Q2? And the answer lies because of this gentleman. Julian Y03 DAC/VA3 IUL is an electrical engineer whose website contains a vast amount of useful links as well as his projects. I have a link to Julian's website on the Popcorn Electronics blog. From Julian's work, I learned that these medium power audio transistors, such as the BD139 or the BD135 that he used, offer low flicker noise with low current, perfect for my VFO. All right, please view Q1, which is arranged as a Colpitts oscillator. Let's think about the internal or intrinsic input capacitance of this transistor. If the collector current were to increase with a temperature increase, so would the input capacitance, which would cause the frequency of the VFO to go down. To provide some temperature stability, I well regulated the DC supply and applied voltage divider biasing for the transistor, including a 1K emitter resistor. This familiar biasing scheme provides some temperature compensation. Connected to the transistor, I used relatively large value capacitors. I hoped that using these relatively large capacitors for emitter bypass, for feedback, and for connection of the base node to the inductor would help swamp or minimize the effects of any stray or internal input capacitance of the transistor. These are all frequency determining capacitors, and therefore I used C0G, also called NP0, temperature coefficient capacitors to help minimize temperature drift. Let's talk about the inductor. 28 turns of number 28 gauge wire on a T56 dust powder toroid. I cover how to prepare inductors for frequency stability in the other video, but I'll add a couple of things here. When winding powder iron toroids, I'll usually put on an extra couple of turns and then remove the first 2 turns because the initial 2 turns will be the loosest turns on your toroidal inductor. For this project, I boiled 2 inductors and set my timer and boiled them for 5 minutes. I switched off the stove, waited a minute, and then carefully moved the inductors onto a towel, and I left them alone for 5 minutes to cool. I then placed the coils on a towel, blotted them carefully once, and left them alone for an hour to cool and to dry. Due to time constraints, I only boiled once. I then connected my Varactor diodes as well as a 4 to 20 PF air variable trimmer capacitor, and then added small C0G caps so that I was around 3.5 megahertz in frequency. I'll discuss the second half of the schematic, the tuning circuitry. Online or in the amateur radio literature, you'll see lots of examples of people using either rectifier or Zener diodes or even LEDs as voltage variable capacitors. If you reverse bias the PN junction of a diode with a DC voltage, you will get a voltage-dependent capacitance in many cases. Because this VFO is exclusively tuned by variable capacitance diodes, we're going to use the special purpose diode called the Varactor. I originally wanted to use the BB535 Varactor, but that didn't work out. There are 2 basic types of Varactor diodes, abrupt and hyperabrupt. The hyper-abrupt diode is what we're using. They have a large delta C for a small voltage change, and they're great when you have a limited DC voltage like we do. We have a maximum tuning voltage of 12.3 volts DC. The abrupt type of Varactor has less delta C per voltage change. They tend to have higher Q and lower distortion, and are often used where low-level signals occur, like the front end of a receiver, and you can use up to 28 volts or so on many of the abrupt Varactor's maximum DC reverse bias voltage. On the schematic, you can see we have a left and a right series pair of Varactor diodes. Each series pair, so top and bottom, are arranged anti-parallel. Placing Varactors in anti-parallel pairs avoids forward conduction and even harmonic production. If you think about our tuning voltage at its lowest level, which will be around 1 volt in this case, it also helps prevent rectification. So we never want our Varactor DC reverse bias voltage to go to 0. We want to keep it at 1 volt or higher, or something like that, to avoid intermodulation products and excessive phase noise. Further, I limited the AC oscillator swing across those Varactors. I measured around 8 volts to peak, and I did that primarily by limiting the current of Q1, the Colpitts oscillator, to around 1.15 milliamps. Note that each Varactor anode has a DC path to ground, which is essential. The bottom Varactors are connected to the copper-clad board, while the top anodes have a DC path through the 100K resistor to ground. You may have noticed that the Varactor diodes are surface mount parts. Although I use the BB515, the BB535 is my favorite. I've bought them in Canada, in the US, and in Europe in recent years. It really doesn't matter which Varactor you use as long as it's a hyper-abrupt or high capacitance ratio Varactor. I made a breakout board in order to use these surface mount Varactors. I took a single-sided copper-clad board scrap and scored 2 lines in it, as shown. After taking my aviation shears and cutting the ground end of the board flush and level, I soldered it at a right angle, perpendicular, to my main VFO copper-clad board. Easy peasy diode squeezy. I'll now discuss the tuning network. After some decoupling and bypass parts, you'll notice there are 2 pots with a 10-to-1 ratio. Another option is to use a 10-turn pot. However, I couldn't fit one in my Hammond 1590B metal chassis. I originally wanted to use a 50K plus a 5K pot, but I didn't have any 50K pots in stock. A fixed value resistor is placed on the ground end of each pot to try to keep the DC voltage around 1 volt when the pot is fully counterclockwise. I kind of failed on that a little bit, as you'll see in the next video montage. Note I have a 100K resistor that says DVM option. That's actually connected with a wire to a feed-through capacitor on the back panel so that I can monitor DC voltage while I tune. I've got the coarse tuning pot fully counterclockwise, and we're at 3.497 megahertz. I'm going to advance the pot clockwise until we get to the band edge, 3.50. Okay, we're at 3.50. 3510. 3520. 3530. 3540. And now I'll turn it fully clockwise. And you can see we've applied the maximum DC voltage to the Varactors, and we're at 3550 or 3.550 megahertz. I forgot to mention it, but voltage-controlled VFOs are often referred to as VCOs, or voltage-controlled oscillators. The rest of the video is going to be stability testing. I just have 2 still images with a 1-hour time lapse, and then we'll go into video showing some stability at 3.5 and then 7 megahertz. I built this VCO on a bitterly cold day, and the furnace was cutting in and out, and I could feel the room temperature changing. A good real-world test. To start, I took a photo at around 306 and then another at 406, and the difference in frequency was 97 hertz. So at 7 megahertz, that would be 194 hertz frequency drift. My frequency counter has an LED display that shows horizontal banding when you videotape it, so I had to put my camera on manual with 1/20th of a second shutter, and so you're going to see some shaking. My frequency counter is too high to use my tripod, so I'm holding the camera with my left hand and tuning with my right, and it was not easy, so I apologize for the shaking. It was technically difficult to do. 3.5 megahertz measurement. After leaving it at maximum frequency for a few seconds, I'm going to take it down to 35.25.000, and actually quite difficult to do that. My left hand is above my shoulder. I'm looking at the frequency counter through the camera. I've got the slow shutter. My right hand is fumbling around trying to turn these pots. It wasn't easy. In this maneuver, I'm trying to assess tuning resolution. It's actually pretty good. I'm fumbling around, and one thing I can conclude, I definitely need bigger knobs on these potentiometers. There, I finally nailed it. 35.25.000. So now I'm going to take it as close to 35.00 as I can and not spend so much time fumbling around. Got both hands on the camera because my shoulder's getting sore. Okay, I'm going to add the frequency doubler from DJR K04BB. I did add my own transformer and output network. Seven megahertz tests. We're at the highest possible frequency, around 7.100 megahertz. This time, I'm not going to fumble around too much with the tuning. I'm going to target a frequency and then get both hands on the camera to assess frequency stability. I'm going to quickly take it down as close as I can to 7070 and get both hands on the camera. You can actually see it in the reflection on the counter. Now I'm going down as close as I can get to 7035. Now I'm going to target 7020 as close as I can get. It's important to test your VFO across its tuning range. 7008 and then 7000, and I'm sorry this is taking so long. This video is really dragging on. I apologize. I think I feel quite happy about the temperature stability of this particular VCO, and it's encouraging, and it's been fun, and I've learned quite a lot. There's one item left, and that's to go over the transistor Q3. It'll only take a minute. Q3 is a very basic amplifier with a little bit of degenerative feedback. I used a 2N4401 in this slot. Probably should have used a BD139. However, I couldn't fit it on the board. I was really crammed at this point. My personal limit for collector current for Q3 was 6 milliamps. As you can see, I biased it for 5.9 using standard value parts. In order to get a perfect sine wave out and to get the 10.9 dBm output, I would have had to bias this amp for 14 milliamps. However, I chose not to. I chose to bias it for 5.9 milliamps, and in doing so, I incurred some distortion. I forgot to mention earlier that another goal of this project was that the entire current draw was less than 10 milliamps. Turned out to be 8.7 milliamps, so I was on target. It's been great hanging out with you. I enjoy popcorn electronics and simple and fun circuitry. Thanks for watching to the end, and I wish you very well. Cheers.